This week we are talking about waves and tides. Yes, you should be taking notes. And as we just did for our Do It Now, let's do a quick diagram of a wave. And you guys all knew this pretty well, so this should be pretty easy. I'm going to go through it relatively quickly. A wave is actually the transfer of energy. The waves we'll be looking at are the transfer of energy through water, and the energy moves, not the water. As we watched yesterday, Tim and Moby tell us, and as you know, waves can also travel through other things. The earthquake waves travel through land and buildings and stuff that they knock down sometimes. Waves can travel through, sound waves travel through air, light waves travel through empty space. So there are many different types of waves, but it's always energy moving from one place to another. So, definition of wave. Then as we look at the parts of a wave, this is a graph, and this line here in the middle represents zero energy or rest. So on a calm sea, or with no earthquake whatsoever, you're just going to have a flat line. And then we can draw just a really basic wave here that would go up and down like this. And then labeling, some of these things are pretty obvious. The crest is, of course, the highest point of the wave, highest point above zero. And then the trough is the lowest part. Again, pretty easy to identify, the crest and the trough. And then the wavelength is how long the wave is, pretty easy word. And the easiest way to measure it is from crest to crest, because those are easy places to see. Or you could measure it trough to trough, or you could actually measure one complete cycle. So starting at zero, going up, and then going back down, and then back to zero. That's also one wavelength. And if we put our line here showing wavelength, which would be from here to here, with my wavelength label. This one? Yeah, there should be another one, but that's okay. So, but if we took this wavelength here, we could show that it's the same if you went from trough to trough, from crest to crest, or from zero to zero. And of course, it's a little bit of an imperfect wave there. But that, of course, is wavelength. All right. And then finally, oh, and then amplitude, as we talked about, the amplitude is going to be how much energy the wave has. In sound, it's how loud the sound is. You amplify sound, you make it louder. And so it's the distance from zero. So the amount of energy, and it's the distance of zero to the top of the wave, or of course zero to the bottom. Okay, so pretty straightforward there. Again, we went over all that, and it seemed like you guys knew that. Frequency is how many waves per second. And again, it seemed like most of you had a good understanding. A higher frequency would be more waves per second. So a higher frequency would look like, let's do a different color. Higher frequency would look like this, and would be a higher sound. A lower frequency would be like this and would be a lower sound. How many waves per second, which they measure in hertz, which is Hz. I probably won't ask you that, so don't worry about that. Okay, we talked about tsunami waves, and I believe I drew you a picture of this. As the wave approaches shallower water, there's the same amount of energy in a shallower ocean, and so it moves upwards. And I'll show you that again with that picture, because basically the amplitude is the same, but because the water is shallower, the water gets pushed up. And so that's the tsunami waves, and we'll skip that waves and erosion for right now. This is just a picture out of the book. It seems like sometimes that the water is moving, but in fact, the, see, now that's saying wave height. That's, oh, wave height is from the trough to the crest. But in science, you never use wave height. You always use amplitude. So just ignore that. That's kind of stupid. And then what's happening here is the water is really just bouncing up and down. So if you imagine a piece of stick or a little piece of wood sitting on the water, when the waves go by, it just goes up and down. It doesn't move with the wave, just the energy moves, not so much the water. All right, let's, whoa. Well, it will eventually drift because of currents and winds and things like that, but it doesn't come in on the top of every single wave. All right, oh, so this is what I was talking about. So here's the amplitude of the wave, and when you've got your tsunami, it starts out here in the deep ocean, whoa, and then you can see what's going to happen as the wave comes in. Pretty soon you have this much energy in this much space, and that's, of course, where you get problems. So, all right, questions about any of that? Pretty straightforward. You probably saw some of this stuff in 6th grade. That'll be on Friday's quiz. Piece of cake. Excellent. Let's go on to the trickier part, which is tides. Yeah, yes. Tides. So tides, especially for people like us that live here in Colorado, tides, I think, are a lot harder to understand than if you live near the ocean. Has anyone here ever lived near the ocean? Yeah. So, and even you lived in the ocean. That's nice. Did you live under the sea? Hang on here. Let's get back to here. Okay. Okay, so let's get back to here. Now, the reason I ask is those of you who have lived near the ocean, or maybe even if you spend a lot of time in the summer near the ocean, people know the tide charts. They know when the high tide and the low tide is going to be. You know the moon phases. The moon doesn't rise at the same time every night. The moon doesn't set at the same time every morning. Sometimes it's up during the day, sometimes it's up during the night. The high tide occurs, one of the high tides with the full moon and the other one with the new moon. But that time of the high tide is always changing. So if you live near the ocean and you want to go swimming, if you want to go play in the waves, it's really important to know if the tide is coming in or if the tide is going out. As the tide goes out, there can be dangerous currents. You need to know which way the water's going so that you are safe. The ocean, as you know, is very big and very strong. So people that live near the ocean know a lot about the tides and the tide charts. They know how to read the tide charts and generally are very aware. You go to any of these beaches and there's these big charts that show all these times, and at this location the high tide is going to be this time, and then a little bit down the coast, even just a couple miles away, the high tide's at a different time because of the shape of the land and that sort of thing. So the tides are caused by the gravitational pull of the moon and the sun. And again, we saw this, of course, in our Tim and Moby video, and you can see here that this picture doesn't even have the sun. The moon, of course, is here. The sun is way bigger than the moon, but the moon is way closer. So the moon is going to have a more pronounced effect on the tides. And it seems kind of hard sometimes to imagine, but actually the gravitational pull is actually pulling the ocean, and of course this is not to scale, to make a little bulge there, and that's high tide. This is the North Pole. We're looking down on the Earth. And then, of course, since the Earth is rotating, since the Earth is rotating on its axis, as the Earth rotates, let's see if we can get this to go around, like this, the area where the high tide is changes. And since, of course, the Earth rotates once every 24 hours, causing night and day, you get one high tide. Actually, you get, most places get 2 high tides and 2 low tides each day. There's some pretty good animations. I'll see if I can find you one. Otherwise, if you just look up online for animations of the tides, it really helps to actually see that instead of just reading it. So tides caused by gravitational pull. The ocean is pulled, making a slight bulge. Earth turns. Okay, so that's what we just did. Most places too high, too low. And the highest tides are going to occur at the full moon and the new moon. And we have a nice picture here from the textbook to explain that. And also, and this is, I don't know where these names come from. To me, they're always a little confusing. There's something called the spring tide and the neap tide, and you'll need to know which is which. And so let's look at the next picture to tell us. All right, this is again from the textbook. The spring tide has a bigger difference between high tide, that should be, and low tide. And so a spring tide is going to occur during the new moon or the full moon. And again, this is right from the textbook. And the reason why it's a much bigger tide, so this is going to be the highest tides, is because the sun is here and the moon is here, so it's making a really big bulge. This one, the neap tide, which again is kind of a strange word, the moon is here, so the moon's pulling this way and the sun's pulling this way. And so this is not going to be as big of a tide. And the way they describe it is they say there's a smaller difference between the high tide and the low tide, but basically it's not as high of a tide. Whoops. Okay, don't know where that went. So spring tide, neap tide, and I don't know, maybe you could remember it by the springing is jumping up or something. So that's a really big one, and neap sounds like weak. I don't know. It's something that's easy to get wrong. But so the spring tide is going to be new moon and full moon. So this is just showing you the tides are going to be roughly on a 4-week cycle, just like the phases of the moon, which we'll talk about in a couple weeks. So this is just going to show you week 3, then you've got a full moon. And even though the moon and the sun are opposite here and here, they're pulling here and here, so you're going to get another spring tide, another springing, jumping, large tide. And then this is almost exactly the same before it was here. So then you get another neap tide. And we actually talked about this a little bit when we talked about hurricanes, when we talked about tsunamis. If you have one of those huge storms, at the same time you have a high tide, then your storm surge is going to, the water coming in land is going to be much bigger, right? Because you're going to have, the tide is already high, plus the storm or the tsunami is bringing in more water. Whereas if it's at a neap tide, you're not going to have as big of a difference. All right, questions about that? Okay, so that's really most of what I have. I'll see if I can find an animation to show it to you. Again, we'll go over this in a little more detail, and we have a video tomorrow. Any specific questions on this? And looking online too, if you just Google search, take a look, you'll find different pictures, different animations, and I think it helps to look at different pictures, not just one picture, because the different things I give you on the quiz, it's not always going to be the same picture. All right, that is tides and waves.